Hi everyone, welcome back. This is the last section that we're going to cover today, and these are odd and even functions. So, there are kind of two definitions for odd and even that are equivalent. The algebraic ones are given first. So if I give you a function, ask you it's odd and even, you should plug in negative x in and see if you get the right hand side. And we'll see examples of that in a second. But these odd and even functions also correspond to symmetry of the graph. So odd functions are symmetric about the origin for every point on the graph, and even functions are symmetric about the y-axis for every point on the graph. So there are some very well-known common prototypical examples. So let's start with even, since that's a little bit easier to draw. And so we're going to look at f of x equals x squared. And so let's prove that it's an even function. If we take f and evaluate it at negative x, that gives me a negative x all squared, which is just negative 1 squared x squared, which gives you x squared, which is our original function. So therefore f of negative x does equal f of x, and it's even. So, even function. So let's look at its graph. So we'll make these one here and one here. So here's the origin. Here is 1, 1. Here is 2, 2, 3, 4. And notice that we get all these points on the other side of the y-axis. And if we look at all the points here, this is 1, 1, this is 2, 4. These points on the other side just have their x coordinates changed in value. So this is 1, negative 1, and this is negative 2, 4. And that's symmetry about the origin. Or not about the origin, but about the y-axis. And so that, notice that even functions have the property that I claim. And so let's do the example of odd. So if x squared is even, then it turns out that x cubed is odd. So let's look at f of x equals x cubed. And again, we'll draw this so it's easy to see. But I do need a little room because 2 squared is 8. So we need to have at least about 16 squares. So again, we'll have the origin, we'll have 1, 1, so we'll just leave these squares be 1 this time. So we have 0, 0, 1, 1, and negative 1, negative 1, and then 2 will go all the way up to 8, so 2, 4, 6, 8. This will be 2, 8, and then we'll have to go down to negative 8 over here, so 2, 4, 6, 8, so this is negative 2, negative 8. And one of the way to tell if a function is odd is that if you take points that like 1, 1 and negative 1, negative 1, where both coordinates are at opposite sides, and you draw a line through them, it will always go through the origin. That's what it means to be symmetric about the origin. So if I draw a line from here to here, it should go through the origin as well. We haven't proved that this is an odd function. So a picture is not a proof. So let's prove it. So f of negative x in this case is negative x all cubed, which is negative 1 cubed times x cubed, and negative 1 cubed is negative. And we have x cubed, which is our original function f of x. So notice that we get f of negative x equals negative f of x, which means that we have an odd function. So one of the things you're going to be asked to do is to prove whether a function is even, odd, or neither. So let me just come up with a random example here, and we will see what it is. So f of x equals x cubed plus x squared. So solution, to see if it's odd or even. We always evaluate f at negative x and see what we get. And so we'll have negative x all cubed plus negative x all squared. And notice that the first term has a sign change, but the second term does not. So this does not equal f of x because we have a sign difference here. And it does not equal negative f of x because if we were going to equal negative f of x, this wouldn't need a sign change, which did occur, but we didn't get the sign change here. We needed to factor out the negative. So this is a neither function. Alright, we'll have more examples on the in-class assignment, so I will see you all in a few days.